Welcome to an example of classifications of functions such as one-one function, onto function, bijections, and invertible functions. Check the injectivity and surjectivity of the following function. F defined from R to R given by f of x equal to x square. This time, both domain and codomain are given to be set of real numbers. And each element of domain is related to the image by this rule x square. That is, image of 2 is 2 square, that is 4. Image of minus 5 is minus 5 square, that is 25, etc. We need to check this rule, this function is 1, 1. What is 1, 1 function? A function f defined from set A to set B is defined as 1, 1 function or injective function if distinct elements have distinct images under that rule. That is, when you take distinct elements in the domain, their images should also be distinct, which can be interpreted as when x1 and x2 are unequal, their respective images f of x1 and f of x2 should also be unequal. That is what distinct elements mean. If you take an x1 and an x2 which are unequal, then their respective images f of x1 and f of x2, they should also be unequal. Or in case the images happen to be equal for some elements x1 and x2, then the x1 and x2 should be equal. Both of these ways we can interpret this definition. Once more, when the elements x1 and x2 are unequal, the images should also be unequal. In case the images are equal, then the elements x1 and x2 should also be equal. These are two interpretations of the definition. While proving it, while checking it, whether it is 1, 1 function, we can use either of these. I am going by the second interpretation. To use in a general element method, let the images be equal. For some x1 and x2, let the images be equal. For some x1 and x2 of the R, that is a domain. Which means, what is f of x1? F of x1 is x1 square. F of x2 is x2 square. So if you take these two images are equal, that means x1 square is equal to x2 square. Please be cautious. Don't just take off this square sign and write this implies x1 equal to x2, which may not be true. So what we need to do is simplify this equation. x1 square minus x2 square is equal to 0. Factorize it. That is, x1 minus x2 into x1 plus x2 equal to 0. This quadratic equation is being factorized. Now, this product can be equal to 0 by either having x1 minus x2 equal to 0 or x1 plus x2 equal to 0, which eventually implies x1 equal to x2 or x1 equal to minus x2. Here we notice, whenever the images are equal, we should have had the only possibility that should have implied that x1 and x2 should be equal, no other way. These images could be equal only by having these two equal. Only if it happens so, we can say the function is 1, 1. But what happened here? These images can be equal by another way also. Is it possible x1 and x2, x1 is negative of x2? Yes, it's possible. x1 and x2 are taken from set of real numbers. So this is possible for set of real numbers. Whereas, if the domain was set of natural numbers having all positive numbers, we would have said this part is not possible. But here, The domain is R, set of real numbers, having negative as well as positive numbers. So this kind of an equality is possible. So these two images could be equal, not only by having these two equal, but also another way. So this could not strictly imply the equality of the pre-images. Therefore, we conclude this function is not a 1-1 function. It did not follow the definition. It's not a 1-1 function, or in other words, it's not injective function, not injective function. The same concept, the same proof could be written using a numerical example, a counter example. I take x1 and x2, two numbers which are unequal. The other interpretation of the definition. Let me take x1 as 2 and x2 as minus 2. Obviously, they are unequal. 2 and minus 2 are unequal. Now, let me see what is f of 2. F of 2 is 2 square, that is 4. What is f of minus 2? F of minus 2 is minus 2 whole square, that is also 4. So, having these two numbers unequal, the images are coming equal. These two images are equal. That is, f of x minus 2 is equal to f of 2. So, having these two elements unequal, we happen to land at the images equal, which goes against the definition of 1-1ness. Therefore, this goes as a counter example. This numerical example counters the definition. Hence, the function is not 1-1 function. It is not 1-1 function. To prove this, we can go either by this general method or by this numerical example, which is called counter example method. Now, let us check whether the same function is an onto function. What is an onto function? A function f defined from a to b is called onto function or surjective function if for each element y that is taken in the codomain, for each element y that is taken in B is the codomain, there it should exist at least one x in the set A, that is the domain, such that the image of that x is y itself, or f of x is y itself. These three stages we need to check. Let's begin. Let's begin with an element taken from the codomain. Let y be any arbitrary element taken from the codomain. Now, if possible, let this y be written as x square. If possible. Is it possible? Yet to be checked. If possible, the y that we have taken be written as x square, which implies x is equal to square root of y. Now, the x that we have calculated, is it available in the domain? That we need to be checked. This x that we have calculated, that should exist in the domain. Does it exist? Look, if y is any real number, for any real number, the square root need not be a real number. Why not? There are examples. Take y as minus 5 and square root of minus 5 is the x, which we cannot find in set of real numbers. Therefore, the second stage is gone wrong. We do not get a corresponding x here. That itself is enough to say that the function is not an onto function. Now, the same procedure could be done, same proof could be done using a numerical example, a counter example. How is that? I'm taking a y is equal to minus 4. A numerical example, y I'm taking from the codomain, minus 4. Now look, is it possible to have an x in the domain? For what x square would become minus 4? There is no real number whose square can be minus 4. So, there is no x belonging to the domain. such that x square could be equal to minus 4. It's never possible. This goes as a counterexample. This numerical example is a counterexample, an example which goes against the definition. So we conclude that the function is not an onto function.